R. Buckminster Fuller was one of the last century's geniuses, probably best known for his invention of the geodesic dome. If you've been to the Epcot Center, then you've seen one already. It's the big spherical building with dimples all over it. When he was about 27, his young daughter died, and this caused him to experience a period of depression. He decided not to talk for a year, and this may have helped him picture things in his mind without the interference of language. A great deal of his thinking seems to have used mental pictures directly instead of abstract, symbolic systems like English and mathematics, although he was certainly up to speed in both of these areas too. The material in this talk comes mostly from his book, Synergetics, Studies in the Geometry of Thinking. At the beginning of the book, he writes that he doesn't care if anyone understands it or not. He just doesn't want them to misunderstand it. So the book seems somewhat obtuse to say the least, but is worth the effort it takes to read it. A big concept in Fuller's thinking is the idea of synergy. He used to describe it as the behavior of whole systems unpredicted by the behavior of the parts making up that system. For example, you can make a metal alloy that has a much greater tensile strength than the component metals that have been melted together to make the alloy. Many things are greater than the sum of their parts, so to speak. Fuller went so far as to claim that this is the basic organizational plan of the whole universe, so he described the universe as a hierarchy of synergies. Since this concept is so central to his thinking, let's consider a few more examples. If you think of a chemical compound, say water, as the system you are considering, then it has certain behaviors and characteristics that are very different from its parts, which I will call subassemblies. Its immediate subassemblies are oxygen and hydrogen, and they are always patterned in very specific ways in order to get the synergy of water, namely 2 atoms of hydrogen for every atom of oxygen. You can explode hydrogen and breathe oxygen, but you don't do either one with water. If you consider hydrogen as the synergy under observation, then you find it consisting of 1 electron and 1 proton, the behaviors of which are again quite different from the behaviors of hydrogen. At each step of this small hierarchy, you find the same organizational idea, a whole system made up of subassemblies patterned in very specific ways. A couple more examples. Your body is a hierarchy of synergies that goes somewhat as follows. If you pattern the subassemblies of cells in certain ways, then you get tissues, such as lung tissue, liver tissue, heart tissue, etc. If you pattern the tissues together in certain ways, then you get organs like the liver, the heart, and so on. If you pattern organs together in certain ways, then you get bodily systems like the circulatory system, the nervous system, the digestive system, etc. If you pattern the systems together in certain ways, then you get a body. The same thing happens in outer space. If you pattern a bunch of planets, moons, comets, and asteroids together with a star, you get a solar system. Then if you take a bunch of star systems, let's call them that because they don't all have planets and moons, and put them together, you get a galaxy. A bunch of galaxies as subassemblies gives rise to the synergy of a universe. One final example, an automobile. The synergy of the whole system we call a car is that you can ride down the road in air-conditioned comfort. Consider how different that characteristic is from the characteristics of its various subassemblies, such as a lug nut or a steering wheel. Consider also that all of the parts of a car unassembled would weigh the same as an assembled car, and for that matter would involve the same number of atoms and molecules. This helps us to see the importance of the patterning of the subassemblies in creating the synergy. In fact, it is often the case that subassemblies, or parts, can be made out of different things and still work, but the pattern must still be followed. If you had a plastic heart that worked, you'd still be okay unless it got put in the wrong place. That is to say, unless the patterning of the subassemblies got messed up. Okay, this may be interesting and all that, but so what? Who cares, and why? Some very important things follow from this insight for the best doing of science. First, Notice that the very selection of what a whole system is somewhat arbitrary. The observer figures prominently in deciding what constitutes a system. If you want to analyze an air conditioning system, for example, then does the system include the electrical station generating the power, or does the system stop at the outlet and the wall? Not factoring in the role of the analyzer or observer can mess up your results down the road. The very nature of our existence imposes certain perspectives on anything we observe or experience just because of our size, our senses, and how much time we take up. Consider how different the same things would look if each of us were the size of the sun, or if we lived millions of years. So there are zillions of zoom levels between the smallest things, like quarks, and the biggest, like galaxies. Usually we have to decide on a particular zoom level, and at the very least we should be aware that whatever we're dealing with is happening at a certain zoom level in a hierarchy that goes up and down from where we are looking. The second thing Fuller's insight helps with is that we can more clearly know just what it is exactly we're looking for if we know that we're looking for a synergy made up of patterned subassemblies. One of my favorite examples is the field of optics, where the synergy is the experience of vision. Notice that defining this as the synergy we want to understand includes the observer, and that the synergy is the experience itself. With this as the synergy, the subassemblies are light and its sources, or reflected light and its reflectors, eyes, optic nerves, the occipital lobe, and so on. Once we understand how these subassemblies of the experience are patterned together, or related, then we can use the system to our advantage. In the case of optics, our understanding of the system has permitted all kinds of dividends like movies, TV, microscopes, telescopes, and so on. If we are looking for patterns and or connections between and among subassemblies, and realize that each subassembly in its turn is a synergy with patterned subassemblies below it, and that it may in its turn be a subassembly of a larger synergy, then we are better positioned to avoid some of the things science has lately been criticized for. In particular, we either avoid reductionism or at least become aware of it. We can also find patterns above and beyond cause and effect if such exist. In statistics, for example, correlations can be useful even if cause and effect cannot be established. By correctly ferreting out the patterns by which subassemblies are arranged, we are in general finding out the rules that govern the operation of the system. Such rules can be the basis of experiment, prediction, invention, and so on. To give a sense of how Fuller did his thinking, I will relate one thought experiment he did which will also shed some light on features of system organization. You may have heard that Einstein also did thought experiments leading up to his relativity theory. In this one of Fuller's, you must first imagine a void, which you can do by imagining a universe with nothing in it. In other words, an empty space, now populated with a sphere. If that's all there is, there would be, I think we can agree, a serious lack of information. Don't forget, there's a reason why we're said to be in the information age. Some say there isn't really anything but information, so this might be important. Anyway, almost as an aside, Fuller notes that unity is at minimum 2, by which he means, even where there is only one thing, like our sphere, it still has an inside and outside. So even if there is only one thing, you can go in toward the center or out away from it. But so far in our thought experiment, there isn't anything to go in or out, so we hardly have any information, and certainly no system. To begin building a system, even the most rudimentary kind, you now need another sphere. So let's populate our void with a second sphere. Think about what information could be available in this situation. There is really only one substantive bit of information, and that is that there is an other. from which our first sphere can now come by a sense of itself, which it couldn't have done before. It can get no certain information about the other sphere except that it exists. It could be moving or not, but our first sphere couldn't be sure, because if it expanded and got brighter as it moved away, it would appear to be standing still, and if it were approaching and getting smaller and dimmer at the same time, it would still appear to be stationary to the first sphere. Now assume that the two spheres make contact, and let's make them both the same size. As long as they are in contact, they can roll all around each other, but as long as they are in contact, they must function together as a very rudimentary system. Now some information is also available about the size and location of the other sphere and what it is up to. Now let's make a third sphere the same size and have it join the other two. By join, I mean smack up against them. Now they can only move in one way, and they must do so together. If you have information about the movement of one sphere, you can figure out what the other ones are doing too. Okay, let's go for a fourth and final sphere and put it in contact with the other three. Now the spheres are locked as far as the movement of any one of them is concerned, and all four must work together as a system in order to do anything at all. Fuller drew such conclusions as that the tetrahedron, formed by drawing lines from all the centers of the spheres, is the minimum fixed structure in four-dimensional space. Triangles are fixed structures in two-dimensional space, but can't really exist without height, and if they have height, then the corners can be picked up so they aren't fixed. Actually, he wouldn't draw lines because he didn't believe in abstract stuff. Instead, he made actual, real-world models of such things out of metal rods. This should give a fair sense of the manner in which Fuller did his thinking. I hope this talk has been useful to you, and if you find that you understand what has been said, then you might want to think about whether this sort of thing could be taught to young students in school. One is tempted to say that, were society in general much more interested in education than in stuff, we could even imagine a society where useful information replaced advertisements on TV, for example.